For what we have here, we are looking at things called logarithms, where a logarithm is, for our purposes, defined as the inverse of an exponential function. So we have that if b raised to the power x is equal to y, then that's equivalent to logarithm base b of y is equal to x. And hopefully at this point, logarithms are all perfectly clear and you don't need any more work on this because, hey, it's easy and like this is the only video I need to make for this section because you know everything by now. Just reverse exponentials. Simple. No, of course not. Of course, when you look at this sort of thing, you see these all new letters and like the fact that the function has a whole name almost to itself, and like the subscripts are a problem. Nobody likes subscripts the first time they see them. It seems like things are getting flipped. Why are they getting flipped? Why is the b down here and the x over there? What happened? Well, let's actually talk a little bit more carefully. So let's say that someone asks you the very reasonable question, what power of 2 is 8? In other words, they ask you to solve an equation like 2 raised to what power x is equal to 8. And you want to find x. And again, this is not really that normal of a question. Maybe if you're really into math, someone might ask you that. But even if you are really into math, they probably wouldn't ask you that because, well, it's not that hard. It's not that interesting. It's basic understanding of exponents, that what you need to recognize here is that 2 cubed is equal to 8. So, well, x equals 3. Not super clever, not super thoughtful. But again, we want to get a little bit more clever, we want to get a little more thoughtful in terms of what this means, in terms of what it is we're actually looking for with that kind of exponential relationship. Talking in our language from growth rates that we mentioned a couple times in 4.1, we could instead ask this as, if we have some fixed growth rate of 2 units, how long does it take to get 8 units? And our answer would be 3 units of time, whether that's seconds, hours, days, minutes, years, 3 somethings. But, okay, that was still not very hard. I have a little bit more meaning there maybe, but it's not a whole lot of difficulty. So let's say we kick this up a notch, and instead of asking what power of 2 is 8, we ask what power of 2 is 9. Looking at something like that, it's a lot less obvious, right? You know, it's just a tiny bit bigger on the left-hand side, but, excuse me, that'd be the right-hand side. No, I'm backwards. It's one question. Ignore that. But point is, it's not entirely clear because, hey, 2 is not a factor of 9, and in particular, 9 is not a power of 2. So if we wanted to find that exponent x, it'd be something between 3 and 4, but the exact value, not so clear at all. You've got something that seems like it's only a tiny bit more difficult, at least in terms of numbers, but it actually turns into something a lot less manageable. And then, for that matter, we could talk about something that's a lot less rational on this side, and say we're looking with the natural exponential. We want to know what power of the number e, which is about 2.72, is equal to 2. Well, okay, that 2 is really easy, but e is not itself very nice. And other than a couple of very special cases, we shouldn't expect to put in nice powers to be able to get something reasonable out of e other than things in terms of e. So, well, it's not so good. It's not so clear. It's not so manageable to at least do this stuff doing mental math processes like we had up here. Because we know what's going on there. At least we should have some idea after we've seen it that it makes sense, because maybe we don't have all of our faculties there with exponents just yet. It takes practice. Those two, though, even I wouldn't look at that and say, it's dead obvious what value we're looking for. And with these kinds of ideas, we get into the relationship between exponentials, things with numbers raised to powers that are variable, and what we call logarithms, where the ideas here with exponentials and logarithms to describe special kinds of relationships are said to date back to Babylonian mathematics, but the specific notation of calling it a logarithm comes from the Scottish mathematician John Napier in 1614, where he was dealing with things that he called logarithms with the roots there being Greek logos for proportion and arithmos meaning number. So logarithms were proportion numbers, and he called them that because they were specifically made for dealing with identifying ratios in the context of sine, cosine, tangent, and so on, the trigonometric functions, which should make sense, right? Because trig functions, for what little you might know about them at this point, are explicitly things defined around proportional relationships. And it might not seem like much today because you punch things into the calculator, you ask it, hey, what's sine of 32 degrees? It's not so hard, but back then, if it wasn't a really reasonable value, there wasn't a whole lot of easy ways to get that number besides some nasty approximation methods. His idea with logarithms actually was a big jump forward in terms of how those functions, how those values could be properly described. But he didn't actually have the idea there to connect his logarithms to things with exponentials. In fact, that would be work done by Euler. Like I said, he's pretty important when it comes to math, one of the best of all time. He was the first to actually draw that connection there, which is where we get our more modern understanding of what a logarithm is, which is where this relationship comes from. That for an exponential with base b, the logarithm of base b is its inverse. And that's the way that we think about what a logarithm is, where an exponential says, okay, I've got a number to a power, what does that give me? The logarithmic inverse of it will say, I've got a number, what power gives me this final value? Or if we think about this in terms of growth rates, we could say that we have a growth rate and want to know where we end up. How long does it take to get there? So we're saying here, we know that we have a growth rate of 2 and we're supposed to end up at 8. We can use a logarithm to ask how long it took to get to 8, where we would write that something like this. Because this is equivalent to the equality that the logarithm of base 2 evaluated at 8 is equal to 3. That we are identifying specifically the power that we need, the necessary exponent to end up where we want to. So if we wanted to define other things similar, like these guys similarly, we could look at logarithms in that exact same manner. We could turn these relationships around, where we would say that log base 2, so the logarithm in terms of growth rate 2, that gets us to 9, will have some value x, or that log base e, we have a growth rate following Euler's number, will give us 2 at what exponent x? After what amount of time does our population, say, grow to 2 things, to people, to objects, to bacterium, whatever you would be looking at there? Because when we were looking at exponentials, as I said, for an exponential, what we are answering is a question of how much do we have given a growth rate and an amount of time. Here, we're saying how long did it take to get a final value given a growth rate. It's just a reverse of information, remember? An inverse is just asking the same question in the opposite order. That's what a logarithm does here. That's what we use our logarithms for specifically. So let's just get a quick example in here for how we can actually run a computational type thing using logarithms.